Hello and welcome. In this video, we're going to take a look at one-sided limits and asymptotes. Now, in a previous video, we did look at the definition of a limit and looked at a few graphical examples of how to kind of calculate those limits. And in that video, at the very end, we actually saw there was an example of a function where we couldn't actually say that the limit equaled a value. And it was really just because from one side and from the other side, it appeared that we couldn't be consistent on a single value. That's where we give rise to the idea of one-sided limits. So we've got a limit from the left or a limit from the right, and we can use special notation for those. If you want to do a limit from the left, as x approaches a, we just put a little negative sign as a superscript above the a. That indicates that x is strictly less than a, but is getting closer and closer to it. And from the right, we use a little plus sign, and that will indicate that x is greater than a, and we converge on a only from the right-hand side. And then we can take a look at the behavior of a function in a single direction instead of both directions simultaneously. Well, let's take a look at an example. Here I've got an interesting function, y equals f of x. It has some very peculiar behavior around x equals 1. And we can kind of take a look here. We've got a point at 1, 3, and we've got an open point at 1, -2. So unfortunately, that point actually isn't included on the function. Just as a note, we couldn't have a solid dot at both locations because then it wouldn't pass the vertical line test and this wouldn't be a function at all. Let's take a look at the behavior as we get closer to x equals 1 from the left-hand side. So we'll start with the left-hand limit. We'll use this handy notation, limit as x approaches 1 with a little negative sign to indicate that x is slightly less than 1. So we'll begin with a value of somewhere around 0.5. And picking an x value there will put us on the curve just to the left of that solid dot. And as we converge, getting closer to x equals 1, we can see that the y coordinates will be increasing and approach a y coordinate of 3. And so the limit from the left-hand side would be equal to 3. From the right-hand side, we have to then look at the right-hand limit. So this time we'll be using the notation x approaches 1 with a little plus sign. X is slightly bigger than 1, so we can start with maybe a value of about 1.5. Now, on that case, we'll be at a point on the curve slightly to the right of the open circle. And as we start converging in towards x equals 1, it appears that our y coordinates are going to be dropping and getting closer to -2. And so from the right-hand side, even though we have this open circle, our y coordinates are approaching -2, and that's what we say the limit is from the right-hand side. Now, thinking back to a previous video where we looked at a function similar to this, the two sides seem to have different values, and overall, we would actually have to say that the limit as x approaches 1 from both sides can't equal either of those values. If we tried to say that the value as x approaches 1, if this limit was equal to 3, well then we couldn't get arbitrarily close to 3 by choosing values nearby 1 from the right-hand side. And we couldn't say that the limit of f of x as x approaches 1 could be equal to -2, because we couldn't get arbitrarily close to -2 by choosing x values just slightly less than 1. So that would blow away the definition of having this limit equal to some number, and we would have to say the two-sided limit does not exist. And this gives us a little theorem about what it means for a two-sided limit to exist. And the theorem says that the limit as x approaches a, the two-sided limit, equals L, if and only if the left-hand limit equals L and the right-hand limit equals L. They must match. If either of these one-sided limits does not equal L, then it is impossible for the two-sided limit equal L. So that is an important result here. We have to agree that the left-hand limit and right-hand limits both equal L for the two-sided limit to exist and equal L as well. Now, what does any of this have to do with asymptotes? Well, with vertical asymptotes, you may already be familiar with what they may look like on a graph. A vertical asymptote is when a function seems to jump off the graph and just skyrocket. It never seems to reach a ceiling, it just continues to go off infinitely. Now, that gives us a pretty good sort of description about how we could maybe apply this concept of a limit here. As we get closer to a, let's say we start from the left-hand side here, and we pick a value of x a little bit less than a, and we start approaching a, what's going to happen to the y-coordinate? Starting from here, our y-coordinate just seems to take off and go on forever. Where does it stop? There doesn't really seem to be a value it stops at. It's more of a concept that this continues on infinitely. So it's not necessarily that we actually get closer to infinity, it just continues to grow larger without bound. Now, when we decide to put this into notation, we often write that the limit, in this example, of the function f of x, as x approaches a, from the left-hand side, would be infinity. Now, it's really easy to mistake that infinity as being an actual numerical value, when in fact it's not. So, because this is not a numerical value, this is a bit confusing. In fact, we could also say that the limit as x approaches a from the left does not exist. Which of these is correct? Well, unfortunately, both. We would have to say that this limit does not exist because it does not get arbitrarily close to some value. But we say it equals infinity just to indicate the behavior of the function. So both are correct. When we say something equals infinity in the case of limits, that means that the limit also just does not exist. And this is how we would define a vertical asymptote. We could either have vertical asymptotes as we go off the graph upwards to infinity, or off the graph downwards, in which case we would say negative infinity. So we define a vertical asymptote of f of x at x equals a whenever we have one of a few situations. Either the limit of f of x as x approaches a from the left is positive or negative infinity, in which case that's shooting off the graph upwards or downwards on the left-hand side, or the limit as x approaches a from the right-hand side would result in going off to infinity or negative infinity, or possibly some combination of left and right, both of them or one of them being positive, negative infinity. So there's several different kind of situations where we could have an asymptote from one perspective on the right or left, and many different combinations. Now, in two of these examples, it appears that the left and right limits both agree that both sides seem to be going to plus infinity on one of these examples. So we would maybe just write that the two-sided limit, let's say as x approaches a, would equal infinity. It doesn't mean that the two-sided limit exists, but it does mean that the behavior of the function from both sides seems to be growing without bound off to positive infinity. And in this other example, it appears that the left and right-hand side limits would both be equal to negative infinity. And so since they agree, we could write that the limit as x approaches a from both sides also equals negative infinity. But again, does not exist because negative infinity is not some value that we can get arbitrarily close to. Well, I hope that gives you a little bit of an indication about why we would maybe want to use one-sided limits to be able to explain behaviors of both sides of some value of x. And also, it's nice to have a formal definition for what a vertical asymptote is. That way, rather than having to try to graph a function and try to estimate where a vertical asymptote may be, we can then take a look at limits and see the behavior of what is going to be happening as x gets closer to a value. And if it seems to be growing and growing without bound, then we know it's going to be a vertical asymptote just by looking at limits. Well, that's it for now. We'll be taking a look at many more examples of limits and how to calculate them without graphs in future videos. But thank you for watching.